Okay, so the next thing to discuss is some vector algebra. So we already discussed that a vector A is a collection of elements. This is a vector which has two components, so this is a two-dimensional vector. So in the first and most important element of vector algebra is to introduce the object called nabla. So this guy is called nabla. And nabla is a vector, but it's a vector operator. So that means that each element in it is a derivative. So first one is derivative by first component, and then this is the second component. So if I have just a two-dimensional object, then it's going to look like this. But if I have, three-dimensional object, and I have y and x, z here. So maybe actually I jumped a bit ahead, showing that dx means to derive something by x. And I can also write the same thing introducing the unit vectors. So ex has a length of 1 and has a direction in the x direction. So this is 1, then this red arrow is ex vector. So that means I am deriving everything by x in the x direction. I am deriving things by y in the y direction, and I'm deriving things by z in the z direction. So since physicists are lazy, we usually like this notion a lot. The vector operations that we can do with this nabla object, so the operations start with something which is called gradient. So in a gradient, we apply the nabla to a scalar field. So we say that we have the nabla, which is a vector, apply it to f field, and that's not a vector, right? It's a scalar field, so I am not making any underscore, and so that's going to mean that I am adding together ex with the derivative of f by x plus adding together the derivative of y of f in the y direction plus, oh sorry, that's a plus, plus something in the z direction, that something is a derivative of f. So if I go back to in our notion here, then the gradient is the derivative of f in the first point in the vector, derivative of y in the second one, and the derivative of z in the third one. So please note that when you do gradient, the outcome of that is going to be a vector. You can also apply nabla to a vector field, which is going to lead to two things. If we first do it with the dot product, we have now two vectors, we can do dot product and cross product of them. So if we use the dot product, that's called the divergence. So in the divergence, we have nabla vector dot producted with, let's just call it uppercase F, our vector field. And so this is a vector times a vector, dot product it, so that's going to give us a number, and that number is going to be derivative of f in the x direction by x plus, then we take y direction of f and derive that by y, plus we take the z direction of f and derive it by z. Okay? And then the third thing which you can do is called a curl, sometimes rotation, which is that we take the cross product of this f vector. And so, a vector cross product with a vector leads to a vector. So I'm already starting with the vector notion. And the answer is that is coming from the general fact of how we are calculating cross products. That is, we take the third component of f, derive by the second component, which is y, minus the opposite version. So we take the y component in f and derive it by z. Second one is we derive, so all of them are going to look like this, that we take a derivative of a component of f and we subtract the derivative of a component of f. So the second one, here we put x and derive it by z. So here, that means that we put z here and x here. So we note we did z, x, so this is going to be y, and we did y, z, so that's going to be x, and that means that this is an x and this is a y. So the meaning of these things is for the divergence, kind of the source or the sink of a vector field, while the rotation, as the name kind of suggests, it kind of describes the rotation of the vector field. So we need to introduce one more thing here, that is the Laplace operator. Laplace or operator, also called Laplacian. So Laplacian or Laplace is denoted as a triangle, and it is defined to be the square of nabla. So what does a square mean? That means that we multiply nabla with nabla. So it's a dot product, vector times vector is going to be a scalar. So this is a scalar operator in that sense. And so it means that we take, again, coming from the definition of the dot product, we take the derivation by x twice plus derivative of y twice plus the derivative of z twice. And so on, depends on how many coordinates we have. Of course, I showed all of these with 3 dimensions now.